Study Unit 1, Lecture 5. This lecture will provide an overview of the two basic transistor mechanisms used in power electronics, being the bipolar junction transistor and the MOSFET transistor. More specifically, the type of MOSFET transistor used is called an enhancement mode MOSFET, and the type of bipolar transistor used is actually a derivation from the original bipolar transistor and is called an insulated gate bipolar transistor. The bipolar transistor, or BJT, consists of a set of PN junctions in either an NPN format or a PNP format. The reason a bipolar transistor is called a bipolar transistor because it works by injecting both minority and majority carriers into the silicon. Essentially, both transistor types are used as switches or as gain elements and work by controlling current. This lecture will cover the basics of how the BJT transistor works as well as the MOSFET, and will then focus on how insulated gate bipolar transistors work. As a discrete device, bipolar transistors are not really used in power electronics, but an understanding of the operation is required in order to understand how insulated gate bipolar transistors work, as well as how certain mechanics in MOSFET transistors work. Additionally, an understanding of how bipolar transistors work is required to understand how thyristors work. The basic bipolar transistor consists of two PN junctions stacked into a single piece of silicon. There is a central p-doped region, an N region, and a heavily doped N+ region. The heavily doped N+ region is known as the emitter, the P region is known as the base, and the N region with a heavily doped N terminal is the collector. The heavily doped N region, or the emitter, serves as the main source of electrons which are injected into the emitter base junction over here. Electrons which are injected by the emitter are swept across the P region, across the base, and into the base collector junction into the collector. Ideally, the base should be as thin as possible to minimize the distance that electrons must travel from the emitter to the collector. Additionally, the carrier lifetime should be quite long. In other words, the carriers should not recombine in the base before they reach the collector. Of course, this is not the case, and two things are done to ensure that the electron carriers get across to the collector. Firstly, the base is normally made quite thin, and secondly, and more importantly, carriers can be injected into the base to make up for the deficit in carriers which recombine in the base of the transistor. The relationship between the emitter and collector currents is given by this equation here in terms of alpha, which is the current transfer ratio, which is simply the collector current divided by the emitter current. This is equal to Bt times gamma I, where Bt is the base transport factor and is ideally equal to 1. Gamma is the injection efficiency of the transistor and should also ideally be equal to 1. If both Bt and gamma I are approximately 1 for a good transistor, then alpha will also be approximately equal to 1. The transistor configuration shown here is the common emitter configuration. The reason it's called the common emitter configuration is because the emitter of the transistor is connected to ground. This configuration can be used to define the beta of the transistor, or the current amplification factor of the BJT. The current amplification factor is the ratio of the collector current to the base current. This can be written as the collector current divided by the base current, rewritten in terms of the emitter current and collector current. This is done using Kirchhoff's current law, which states that at this node the base current is simply the emitter current minus the collector current. These factors can then be rewritten in terms of the base current and refactored in terms of alpha, where you have alpha over 1 minus alpha equal to the current amplification factor. What can be seen from this equation is that if Bt and gamma I are approximately 1, then alpha will also be approximately equal to 1, which results in a very large beta. However, if alpha is small, then beta will also be correspondingly small. In power electronics, the BJT is operated in one of two states. There is either the off state or cutoff state and the conduction state, which should be obvious enough. In the conduction state, current will be conducted through the transistor, and in the cutoff state, the transistor is effectively off and no current will pass through the transistor. Or even more simply put, the transistor is modeled as a simple switch, which will either allow current to flow or no current to flow. An important factor to consider when using BJTs in power electronics is the methods in which, or rather the mechanisms through which the transistor will break down. Referring once again to this common emitter configuration, there are two breakdown mechanisms which the transistor will experience as current becomes too large. The first breakdown is a gradual breakdown and occurs between the collector and the emitter. The second form of breakdown happens when the base is also included, and this is a more catastrophic breakdown. In the first breakdown form, holes which are created in the collector are swept across into the base under the very high field strengths. The presence of holes in the base now cause the emitter to source even more electrons into the base to recombine with the holes which have been swept across from the collector. This in turn increases the current, and therefore even more holes are created and swept across into the base, and thus more electrons are swept across from the emitter and injected into the base. This is first breakdown and is normally quite gradual. If the temperatures in the silicon are managed, then this form of breakdown need not be catastrophic and the device will recover once the current is reduced. Second breakdown starts happening when there is non-uniform current density in the silicon, and this can be caused by crystal faults or doping fluctuations. In this case, hot spots start forming in the silicon and the silicon can actually melt, and when the silicon melts it causes irreparable damage to the device. Figure 3.9 from the text shows where first and second breakdown occur. On the IC-VCE characteristic of the BJT, there are several characteristic curves for the device depending on the injected base current. As it can be seen, the device will gradually approach first breakdown as VC increases until it reaches some VCS where first breakdown happens. When second breakdown happens, the required voltage across the collector-emitter junction is no longer relevant and current will just flow through the device. Shown here is the basic structure of a MOSFET transistor. The MOSFET transistor consists of a drain, a source, and a gate. Application of voltage to the gate allows for the control of a conduction channel which forms between two n-doped regions through which current can flow. This transistor, which is an NFET, uses n-doped regions on a p-type substrate. Fundamentally, the MOSFET works as follows. A positive voltage is applied to the gate. This causes a positive charge on the gate structure, which rejects the positive charges in the p-type substrate and rejects them away from the gate. This induces a channel underneath the gate, which is predominantly negative. This allows for negative carriers to pass from the n-doped regions from the source to the drain. This conductive region is termed the depletion region and offers a very low resistance relative to the p-doped region in the body of the transistor. An important parameter in controlling the NMOS transistor is the minimum gate voltage required in order to induce this channel. This voltage is called the threshold voltage of the transistor. At gate voltages below the threshold voltage, there is not a sufficient channel between the drain and the source for current to flow correctly. Shown here are the idealized MOSFET transistor characteristic curves. It is a plot of the drain source current versus the drain source voltage for various values of gate source voltage. So for each fixed gate source voltage, the current will increase, forming this curve. The transistor will operate in three regions. There is the cutoff region where no current flows whatsoever, and essentially that region sits over here, and that's where IDS is equal to 0. The second region is the triode region over here. In this region, the current through the transistor has an almost linear behavior before it approaches this boundary over here. During this phase, the current through the transistor is not current and is a function of VDS. The second region and last region of operation is the saturation region. In this region, ideally, IDS is constant for all given VGS, regardless of the value of VDS. Essentially what happens is, as the transistor starts turning on, the current will eventually plateau and remain constant regardless of the drain source voltage. For each region of current operation of the MOSFET, there is a set of describing equations. In the cutoff region, in other words, where IDS is equal to 0, this is the case where the gate source voltage is less than the threshold voltage, and the gate drain voltage is also less than the threshold. In this case, there is no channel in the MOSFET and no current can be conducted. The second region of interest is the triode region. In the triode region, the drain source voltage is less than the gate source voltage minus the threshold voltage. In this case, the transistor current is given by a square law behavior. K'N is the transistor characteristic, W is the width of the channel, L is the length of the channel, and VGS is the gate source voltage, VT is the threshold voltage, VDS is the drain source voltage. Finally, in saturation, the drain source voltage is larger than the gate source voltage minus the threshold voltage. In this case, the transistor current is almost constant. It's important to note that the behavior of the transistor is heavily determined by the geometry of the device. In other words, the ratio of the width of the device to the length of the device, as well as the properties of the silicon in the device, which is determined by the factor K'N. When the transistor is operating in saturation, this is considered from a power electronic standpoint as the fully on state. In this state, the transistor is normally considered purely resistive, with the on resistance as a sum of the epitaxial region resistance of the silicon, the channel resistance, which is the resistance of the channel under the gate, and which is modulated by the gate source voltage, and finally the lead and connection resistance. It is for these reasons that the transistor, or rather MOS transistors, are designed to minimize the RDS on of the transistor to minimize the voltage drop when conducting current. An important distinction between a MOSFET and a BJT is that in a MOSFET, second breakdown cannot occur. This is because the RDS, or on resistance, of the transistor is inversely proportional to temperature, which means that as the current increases, the temperature will increase. What this means is that the on resistance will also increase, thus reducing the current. In other words, if any hotspots form in the silicon, they are automatically diverted away, reducing current and reducing temperature. The MOSFET transistor does not only come in an NFET variation, but also in a PFET variation, where the body of the transistor is an N plus body with the source and drain terminals p-doped regions. The operation of this transistor is similar to the NFET, with the key distinction that instead of conductive N-channel forming between the drain and the source, the majority carrier are now holes. Holes travel slower through the silicon than electrons, and thus the current carrying capacity of a PFET is less than that of an NFET.